right, I want to take a quick look at the syllabus. Since we are getting close to, well, that's interesting. Since we're getting closer to the end of the semester, let's just take a quick look. All right, we talked about electricity and magnetism. We're going to talk about the particles here today. I just want to point out, next week is the week before Thanksgiving. Exam number 3 is on the Tuesday before Thanksgiving. We have one more lecture after Thanksgiving, which will be on the final exam, but other than that, that's about it. There's a reading day, and then the final exam. The final exam is not May 6th. I don't know. It's we can look it up, but it's not May 6th. So we're getting pretty close. This is always a weird time in the semester because it doesn't seem like we should be getting this close to the end since it's only still early November. But because of the way Thanksgiving falls in the fall semester and the fact that final exams generally are only a couple weeks after that, there's really not, or we really are pretty close to the end. We're going to try to, again, cover the rest of the material in basically 3 more lectures today and the 2 lectures next week. We'll basically then only have 2 more labs this week and next week. There's no lab, of course, the week of Thanksgiving, and there's no lab the week after that because of reading days. So we have 2 more labs. Now, if you come on Monday, you'll essentially catch up with this on the Monday of Thanksgiving week. So you've been a little bit offset, where your Monday lab is what we did the week previously, which has worked fine, but this is where you'll get caught up so that everyone will complete the same number of labs. We'll all have done all of the labs. So anyway, I just wanted to go over this because I want to make sure everyone understands. Now again, not a lot of people are here. Those of you who are here, if you're not doing the discussion board, you really need to be doing those. This happens every year, it seems, where I try to emphasize this at the beginning, but there's always 3 or 4 people at the end who go, I didn't realize there was a discussion board. And so you get a 0, and that's going to bring your grade down. If you look at the grading, if you do nothing but take the exams, you can't pass this course. And again, every year, there's 3 or 4 people who show up to take the final exam and have taken the other exams, but haven't been in lab and haven't done the discussion board, and they don't know why they're not passing. There are 3 lecture exams, 200 points each. The final exam is 200 points. That's half of the available points. The rest are the discussion board and participation in lab. All of the assignments that I take up with your names on them and so forth. So I'm sure that most of you that are here are not the ones who need to hear this, which is a shame. But I'm saying it anyway, just in case someone has forgotten, oh yeah, the discussion boards. I need to catch up with those or something. Because that can make the difference. If you look at 100 out of 1,000 points can make the difference between an A and a B. Okay? And that's, again, that happens every year where I give somebody a B who probably deserved an A because they just didn't do the discussions. And there's really not much I can do about that, to be fair to everybody else that did do the discussions, except give that student a B. Same thing, B or C. You may have earned a B every other way, but you didn't do the discussions, and so you end up with a C. And again, this course, I don't give a lot of Fs. I do give a few, but it's generally for people who just don't come, who don't show up. So again, I'm not really speaking to the people I probably need to. But if you do know somebody who maybe isn't making it enough, and again, if you've got valid reasons, I mean, I understand that, and a lot of you are very conscientious about letting me know, and that's not going to hurt you. It's just if you're not coming because you're not a mature student yet, you don't realize how important it is to be in class. You think you can take the exams and do well. Because undoubtedly there are a few classes where you can do that. Just do well on the exam, study on your own, think your time is more valuable or whatever. But this class is about participation, so half the points come from participation. That on one hand makes it easy to make an A or a B. Your exams, and I'll get back to the second exams at the end, a poor exam grade isn't going to hurt you that much if you participate. All right. So I always like to at least mention this as we get closer to the end, because I don't want anyone to be caught off guard. right after Thanksgiving, I'm going to start, accounting for all of these participation grades. I'll go through all of the assignments that I've given in labs and mark who's been there and who's not been. And those things are going to, there's really no way for me to keep track of that too much along the way because it's participation. It's not graded. All right, any questions about the syllabus? Yes?
It's supposed to be December 6th?
Yes, it's not May 6th, as I mentioned. Let's look up what the actual exam date is. I think we've gone through this. All right, so we are a Tuesday-Thursday class that meets from 8:30, or meets at 8:30 in the morning, so it's actually December 9th at 8:30. Now, it goes by the lecture time. Those of you who are in lab on Monday, you still have to come to this final exam, okay? It's not based on the lab time, it's based on the lecture time. You have a question?
Is the final going to be cumulative, and how soon will it?
The final is cumulative, but it's like the take-home portion. And when you come to take that exam, you'll come to South 806. There will be a couple things in South 806 that you'll need to use for the exam, but you don't have to stay there. You can take it to a computer lab. It's a completely open book. Now, if I get the same answer on 2 exams, the exact same answer, I know you've basically just, I'm going to give you 0. All right, I want to see your work, and I'm going to trust that you will give me your independent work. If you discuss something with somebody else, you need to still put that into your own words on the exam. I don't want to see the same answer because that means you weren't thinking. You were just, trying to get it done. So 10 questions, 20 points each. Most will have you, again, watch a video or read an article. Well, not most, some. Some will be in the lab, the types of problems that we talked about in lab. The physics problems, for instance, a couple other things, maybe the maps that are on the wall, geology maps. Different things that, again, you don't need to study for, you just need to be able to interpret what you're seeing. So it's open book, it is comprehensive, but it's like the take-home portion. And you have, basically 3 hours to do it, 8:30 to 11. I give you dinner till 11:30. It says 8:30 to 11. But I'm not going to, again, I don't want to wait all day, but I'm not going to cut you off if you just need to finish up 1 or 2 things. So you got plenty of time. Again, I recommend you bring some headphones because the computer labs don't have them for everybody. And you're going to want to be able to hear the videos without, you can stay in the lab and listen to them too. It's just not enough room for 81 people. There are 81 people still signed up for this course. In fact, I have about that many exams, at least partial exams, some where I still only got 1/2 of it, but there are that many people who may show up for the final exam. So we're obviously not all going to fit in South 801 or 806 at the same time. So you can come and go. Okay, you can leave and do some things, you can come back and do the other things and so on. Okay, and it's always worked out okay. All right, any other questions? December 9th is the date for this exam. All right. Then what we're going to talk about today is the particle zoo. And really, most of this week's content will come in the lab because we're talking about chemistry. And I'm taking advantage of the lab lecture sort of split to be able to get you most of that in lab and talk about something I think is a little bit more interesting in a modern context today in the lecture. Now I'll build it up from a historical perspective that leads to chemistry. We're going to get pretty quickly to modern particle physics. Particle physics is, again, it's a field that is growing really rapidly that has led us to some of the most astounding discoveries and realizations about the world that there are. And so I find this extremely fascinating. I'm really debating, I've done this at the beginning before because it's my really, I think, the most powerful topics to talk about. I've moved it to the end because I wanted to end with a bang, but the last couple semesters, I want to make that things wane, interest wanes, and so forth. So I don't know what I'm going to do with this stuff because I want you to understand this is cool stuff, right? I want this to still invigorate you and make you think, wow, that's really cool. And I've seen that in my class before where people's faces just light up, like, wow, that's really cool. So I don't know, maybe I'll move this back to the beginning. Because just look at the number of people here, right? It's waning, the interest is waning. But for those of you here, again, I hope you are engaged in this because it's really, really cool. And there's a lot of stuff about this that you can find, right? I mean, you can watch documentaries, you can read books on this topic and this is the kind of thing that's happening right now in the news. If you remember the Higgs boson, and this is an interesting example because up until last semester, basically, I would give this lecture, and one of the biggest things, I'll show you a little video in a little bit, one of the exciting things about it was we're searching for the Higgs boson, and if we find it, it's going to be this exciting discovery. Well, we found it. Wasn't that exciting? The point is, what makes that so exciting? Why are physicists just really, you can watch videos, jumping up and down and hugging each other? These are people that are not particularly emotive all the time. But they're excited, they're thrilled about this. People have called this the God particle. And not to be sacrilegious in any way, but just to give it the emphasis of how important it is to the structure of the universe. The Higgs boson gives mass to objects. It makes you and me and every atom have mass. And that's significant. And I always mention, okay, so what? Right? Well, so what is it? Take the last lecture where we talked about the electromagnetic spectrum. We talked about photons of light and electrons. These are quantum particles, just like the Higgs boson. But we've learned to control them. We've learned to control the flow of charge through electrons and the flow of electrons in a battery to create magnetism, generators, transformers, your cell phones, computers, CD, DVD players. All that stuff relies upon the ability to control those photons and electrons. We've controlled them well enough to make lasers and all this other technology that is just astounding. If we can learn to control the Higgs boson in a similar way, the possibilities, again, are beyond science fiction. Imagine being able to control the particle that gives the universe mass. In other words, you can control mass. You think about the movie Lucy, we brought that up last time, and her ability to control the quantum attributes of her body and everything else, and it gave her the ability to basically disappear and be everywhere. That's what we're talking about. That's where that movie came from. That impetus for that movie was the discovery of the Higgs boson. That was the conclusion that those artists came to, that if we could control the properties of the Higgs boson as easily as we control electrons and photons, anything's possible. Anything. So this is, 100 years ago, we were doing the science that gave us control of the electron and the photon. Over the last 100 years or so, we've mastered, at least partially, those forces, those quantum particles. Over the next 100 years, if we gain the same level of control over the Higgs boson, we won't recognize the future. We can't even predict today what might be possible. We can guess at some pretty amazing things, and that's astounding enough. So that's why I think, again, why I save this for the end a little bit, but I also maybe I shouldn't, because this is really amazing stuff to think about. And we'll think about this some more. We're going to think about this in lab next week more, and then after Thanksgiving, the last lecture is going to look at the future and future shock. Yes, you had a question? No?
Yeah, just what are some of the things that are speculated, or it sounds like we're going to get to that.
Well, the easiest things are things like replicators. If you watch Star Trek or most science fiction movies, and you can make food, for instance, instead of your microwave putting food in it and heating it up, you just set a dial and it makes the food for you out of the molecules of the air or whatever. That might be possible. Sending somebody a transporter beam, that might be possible. Okay, now we're going to talk a lot more about wave functions and how much information, how everything really is information, how much information would you have to decode to actually send a human body a distance, may be impossible, but that's at least worth thinking about with the mastery of the Higgs boson. Taking things apart and putting them back together with the forces that hold mass together. So those are the easy ones, because that's been in science fiction for a while. Even without understanding the mechanism that might make that possible, those ideas have been floated before. Yes?
So with this discovery, I mean, like we've already started with space exploration and the space stations and things like that. You think it may be kind of leading into the whole colonization of other planets?
That's potentially true as well. One of the biggest barriers, of course, and we'll talk about this too, is getting from here to another habitable planet. There's two options. We take something close by and make it habitable, so we terraform Mars or one of the moons of Jupiter or something like that. Or we find a habitable planet somewhere else that we can go to. Now, we're finding those planets, but they're light years away. So how do we get there? And really, it may be impossible to travel faster than light. We've got a couple sort of interesting possibilities for that: creating wormholes, warping space-time enough, creating a warp drive, which is basically accelerating space-time itself instead of the ship that you're in. Those are a couple ideas, and if those are ever going to be possible, we will have to master the Higgs boson. Okay, I mean, again, that's the other realm of this, where certain things may become possible that right now are considered impossible. And you may think I'm just being silly, that I'm a sci-fi fan and, I'll go put my pointy ears on and go watch Star Trek, right? But I'm not. I mean, I was a sci-fi fan as a teenager. So I do know a lot of the sci-fi genre going back, but I haven't really been reading sci-fi for a long time. There's a lot of stuff going in that genre that, it bores me, to be honest. And it bores me because this is more exciting, right? I mean, looking at what's actually happening right now and what may be possible because of modern discoveries is more exciting, more interesting than speculating about, science fiction. I mean, I read literature, but I don't read science fiction. Yes?
Doesn't science fiction kind of almost kind of predict the future to some degree?
It does.
I mean, you can think of, I can remember watching, some of these other space movies and various things that they
Right.
I mean, we don't have repligators, of course, but
Right.
they were talking about the various airplanes and being able to, the Concorde and all these other
Right.
things were almost like science fiction at that time, and today it's
Exactly.
commonplace.
No, and that is a point that I want to make. I mean, Jules Verne and H.G. Wells are famous for their science fiction that became reality. We have, and again, I don't mean to diss science fiction. I still do appreciate a good science fiction novel. It's just harder for them to impress me than it was. Ursula K. Le Guin and others. I mean, I read a lot of the 50s Asimov and again Le Guin and others, and it's hard to go beyond their ideas. That was called the golden age of science fiction for a reason. I mean, they really sort of established all of these ideas that we're still seeing come to fruition. I, Robot was Asimov's book. He wrote in the 50s. So there are not a lot of really new ideas in science fiction. There's really not. There's a lot of rehashing the same ideas over and over again. But it's really difficult to come up with something new that's truly, fundamentally a new idea. But as we do gain more things, we can think farther ahead. We are limited to what we can conceive. There is a story, and I think there's some accuracy to this, but when Native Americans saw the first ships sailing across the Atlantic, they didn't see them as ships. They saw them as cloud formations. It was like all of a sudden they were in front of them and they hadn't seen them coming because they couldn't even conceive of what they might have been. So their brains made them something familiar. And the same thing happens to us all the time. I mean, we've already talked a little bit about this in our consciousness, how our brain fills in the details and sort of makes things familiar. Uses what's familiar to interpret things. And a lot of times we're not even aware of this. Now we can overcome this with technology and with education and so on. I mean, we can realize when we're susceptible and adjust for that. But there's a lot of things that about looking into the future that we're still limited in. If you watch Ray Kurzweil or other futurists, people who try to predict the future, they'll tell you basically, we can predict about 10 to 15 years. But that's only because those things are already in the pipeline, right? These things are already being worked on, and someone's going to come up with the discovery that needs to be made to make these things reality. Beyond 15 years, it's useless. And you think, really? Well, think 15 years ago. Let's think back 15 years. What is it? Let's say it's 2014, so we're looking at 1999. 1999, that's a funny year. There was a science fiction TV show back in the 80s called Space 1999. And the whole idea of it was that by 1999, of course, we'd be out in space and we'd be exploring and we'd be running into all these, And it was a decent show. It was a pretty good show. But of course, that didn't happen. What did happen wasn't predicted in the 80s, right? What we have today, in many ways, surpasses what that science fiction predicted for 1999. In 1999, we were still looking at technology. We had the internet, we had computers, we were streaming videos, but we weren't doing it very quickly. I mean, even since Ray Bradbury started writing about the future in the 50s and predicted face-to-face telephone, it was still looking like that was fairly impossible, even in 1999. And now we Skype and FaceTime all the time. And it's because of the control that we gained over the quantum attributes of electrons that led to some technologies that wouldn't have been even possible to conceive of prior to mastering those things or finding those technologies. Yes, Chanel?
Then how can Ray Kurzweil be so sure of the singularity when, some predictions don't come true? Some
Right.
are off, some are on, but how can you be so certain?
Ray Kurzweil's optimism comes from two different things. One is that a lot of what he's expecting is within that 15-year window where he's seeing trends that are already in place that with one or two key discoveries will lead to what he's expecting, which is an artificial intelligence that may spawn consciousness and may lead to the ability to incorporate ourselves with our technology in a way to make us essentially immortal. Now, part of his confidence, however, comes in looking at trends over time and the rate of change, the rate of advance. Without knowing what's going to happen, we do see things happening on an accelerating rate. And you can look back, and he's got a pretty interesting presentation on this. If it's not in one of the discussion boards, I don't know. We'll probably talk about it in the last week after Thanksgiving because we'll probably watch it. But the optimism comes from the fact that we're coming up with innovations all the time. Now, you can't predict beyond 15 years what new innovations might be and what direction those innovations might take us, but you can predict that those innovations will happen. So he's predicting that we're going to continue to make discoveries and develop and have these innovations into the future, that's going to continue to accelerate the way it has for the last 200, 300 years, technologically speaking, and that even without being able to predict them precisely, he can expect there to be some pretty amazing things coming along, and one of them being a computer complicated enough to replicate a consciousness. So we'll see. We'll see. It's a prediction, and it is a likely one. He's likely right, but it's not guaranteed. Nothing's guaranteed. We also have a lot of things that were predicted by science fiction that haven't happened. Right? Where's your jetpack? There's a reason for that, and some of it's in a little bit of a misunderstanding of how these things are going to happen. What we've seen is a revolution in information and our ability to manipulate information, even at the quantum level. What we haven't been able to do is control energy as well as we thought we might. If you think of Iron Man, you think of the reason I went through those comic book laws of physics. The ability to generate enough energy to do some of these things in a short enough period of time is very, very, very difficult. And we haven't had, we've sort of assumed we would master energy. And we've done a lot, but not the way that some science fiction writers predicted. But they didn't predict how much of the universe really is information and how much we can manipulate that and how much we may be creating a new universe in the cybersphere, so to speak. So we're going to talk a lot more about that. Let me get to the foundation of it a little bit before we go to lab, because I do want to talk about what these particles are. I won't be able to show you the longer video, but I might show that in lab this week, but I will show one that I'll end with that I think is just too funny not to show. And anyway, let me get to it. Let's go back in time to the beginning of our thinking about mass and energy. Now, mass and energy are obvious things. We're massive. The objects in our world are massive. It's just a way mass is just a term we give to something that takes up space, that is solid or liquid or gas in some state of matter. Energy is the term that we give to things like heat and light and electricity and so on. Understanding these things fundamentally has taken us a long time, but even way back in Greece, there was one idea about matter that described it as atoms. Matter must be made up of something small. If you take anything and you tear it, you take a piece of paper, tear it in half again, tear it in half again, and again and again and again and again, eventually you've got to get to something that can't be torn in half. The smallest thing. Democritus called it an atom. That's where the term comes from, but it was forgotten for a long time because people had other explanations that worked for a while, but then had to be discarded. They had to be discarded because people like Boyle and Dalton were realizing, as chemistry grew as a science, that when you combine things to make a product, when you create a chemical reaction, you can account for everything in that reaction as if those things combining were little things, little atoms. It's called the law of multiple proportions. Avogadro was able to calculate exactly how many of these little things must be there in any chemical reaction. And so Robert Boyle called them corpuscles. Same idea. There's got to be some little thing, the smallest thing, that is rearranged in these chemical reactions to take reagents, put them together and get a product in the proportions that we know we can get repeatedly, over and over and over again. That's what gave birth to the periodic table, and we'll take a look at that in a little bit, because they could figure out exactly what these little things must be, how big they must be, how much they weigh. All these things could be figured out even without an understanding of what they were. These little things, whatever they were, could be mapped. And that is what we see in the periodic table. Now, early in the 20th century, we began to get a very good picture of just what these little things are. And we got a modern concept of the atom from Niels Bohr and Linus Pauling and others, quantum physicists, who were able to describe the protons and neutrons in the nucleus surrounded by electrons and orbitals, those electrons being held in that orbital by the electromagnetic force, being able to move up and down in different quantum states, and that is what gives atoms their properties. The position of the electrons in these various quantum states is what gives atoms their unique properties. That's a modern concept of an atom, and it can be modeled still like this little solar system model with the electrons flying around the nucleus, but that's really a very simplified model of the atom and how it actually works. And I think more fundamentally, and I'll get to this in a little bit, we need to think about electrons more as energy surrounding the nucleus than as little particles. And to illustrate that, that's a picture of a gold atom at the top, which is pretty astounding that we can take a picture of an atom. I don't know if it looks much like an atom, but anyway, it's an atom. But again, what we're seeing mostly is the energy, the electromagnetic force that is holding the electrons together. There are also forces holding the nucleus together. And so I'm going to show you a map of the various forces and particles that are involved here. I think most of you know the basic atomic model. Protons and neutrons in the nucleus surrounded by electrons in various energy levels. These energy levels can hold varying numbers of electrons depending on, again, the amount of energy that is stable at those levels. So each electron carries a charge. The innermost orbital can only hold 2 charges, so only 2 electrons can occupy that level. The next level can hold 8. The next level can hold 16, and so on. But we start seeing electrons moving. The third energy level can hold 16, but it's stable with 8. So the atom's often at a fourth level before the third level has all 16. And that means electrons can move up and down in between those two levels. And we'll see that in the periodic table in a little bit. But I also want to point out that these electrons, again, it's difficult to think of them as actual little things. We can slow them down and say, okay, here's the electron. But if we do that, we can't measure anything about it. It's just a point in space that we can point to. In order to measure what its properties are, we have to let it go and say, well, it's somewhere in this region. Or, another way of looking at it, it's everywhere in this region at the same time. In other words, it's energy. It's not really a particle. So it's both. We can isolate a single electron. We can control single electrons one at a time. We can treat them like particles. Or we can observe them as energy. And this is where we get to quantum physics. These orbitals are interesting in their shapes. Again, unless you want to take organic chemistry, I don't need to go into a lot of detail about these shapes. Except that some of them, you may notice, the little figure 8 things, give us probabilities of where the electron is at any given time. And there are gaps. Like look at the p orbital down here that has the little ring. The electron can be anywhere within this region or that region, but not in between. Well, how can it be here or here, but not in between? Doesn't it have to go through that space to get from one place to another if it's going to be in one of those two places? And the answer is no, it doesn't. And this is one of those quantum properties of electrons that are very surprising, but absolutely true. And if it wasn't true, you wouldn't have the technology that we have today, because it's that truth that can be used to create switches in your cell phones and so forth that allow for everything to be so, such a complicated device as your cell phone to be so small. Your cell phones, I just pulled mine out as an example because it's not the most modern one by any means. I mean, it's a nice phone, it's a good phone. But what it can do is astounding. Again, back in 1999, we would never have predicted this. It would have been thought impossible to be able to put this capability into a device this small. And again, it's something we take for granted now. But not only can you make phone calls and send texts and emails and take pictures and play games and check your bank balance and all these other things, but again, you can stream movies and TV shows, and I can communicate with my TV at home with this thing. It could use it as a remote control. It's pretty much just whatever you can imagine. You can put that capability into your phone, right? And it can talk to you now, and right, and can GPS. It can guide you anywhere you need to go. It's a pretty amazing little device, and it's not limited by its size. We could make it smaller and smaller and smaller. Put all that capability into a wristwatch, for instance. The limitation is the screen, right? You put all that capability into a little wristwatch. How are you going to read? You could maybe watch a little TV show on a little bitty screen like that, and it would be okay. But you're not going to read text very well, right? Google Glass. You can put all that capability into a little bitty rectangle on the frame of a sunglass, right? And project all those images onto the lens, or into the little corner. And because of how the eye works, that can be perceived, and a lot of detail can be seen in that small little space that you can't really see at a distance. So those kinds of things are coming. Google Glass hasn't been the revolution that some people expected it to be, mainly because you have to take your glasses on and off too often to make that very useful. But who knows what the next innovation is going to be that's going to replace our cell phones with something else, or replace our computers with something else. We'll see as we go forward. But anyway, getting back to the story of the periodic table, if we look at the number of elements that there are, and an element is something that is naturally occurring in a specific ratio. Matter of fact, this is an atom that can be found and can be described, or it can be created and be stable for a period of time. But most of them are these naturally occurring elements at the top, and it's based on the number of protons. When we study these more detail, we realize that each element is unique because it has a unique number of protons. That's the atomic number. So hydrogen has an atomic number of 1. because it's one proton. Helium has 2 protons, atomic number of 2. Now these are always even numbers because protons are whole things. The atomic mass tells us how heavy the atom is, and that depends on protons and neutrons. Neutrons are generally 1-to-1 with the protons, but not always. Hydrogen doesn't usually have a neutron. If it does, it's called heavy hydrogen, or deuterium. Helium, again, if you look at its atomic mass, you'll notice that it's 4. So 2 protons, 2 neutrons. But if you look at most of the other masses, they're not even numbers like that. Even hydrogen's 1.008. And that's because the percentage of deuterium compared to regular hydrogen is very small. But there is some, so when you average it all together, the mass is not 1 or 2, but in between, even though it's a very small number. If you look at something like carbon, 12.01, carbon has 2 isotopes, a stable one and a radioactive one. Carbon has 12 protons, so stable carbon, most of carbon, is 12 neutrons. So it has 6 protons and 6 neutrons. The atomic mass is 12. Okay, sorry about that. When it adds a 7th neutron, we get carbon 13. That's a stable isotope, and it's a little bit heavier than carbon 12. We can use it as a tool to track different things in the environment because it will accumulate. Anyway, there's different things we can do. But as an 8th neutron, however, it becomes unstable. It becomes radioactive. So it starts to lose radioactivity over time. We talked about that when we talked about historical geology as a tool for dating how old things are. I won't go back to that. 2 things I want to point out, and again, I'm way behind where I need to be, but the noble gases on the far right side, with helium at the top, neon, argon, krypton, xenon, radon. These are noble gases because they do not react chemically, and they do not react chemically because they're full. Their energy levels are completely stable. There's no reason for an electron to leave one of those energy levels and go to a different atom's energy level. So they don't react chemically. Now I just gave you the secret to chemical reactions. Most of these everything else has an odd number of electrons in the outermost energy level. In other words, it has the same number of electrons as protons, but not enough to fill that energy level and be completely stable. So they're all a little bit unstable, and that leads to the electrons moving from one orbital to another in order to make those energy levels stable, and that creates charges, or the electrons are actually physically shared, and that creates a covalent bond. So those types of bonds, again, we'll talk about more in lab. We'll come back to that. It also means that there are a number of these elements that not only can share or exchange electrons with other elements, but move their electrons up and down in energy levels. As I said, if you look at the first row, it's only got 2 elements because there's only 2 electrons in that first energy level. So the rows tell you the energy level. The second energy level has 8 in it because that fills that energy level. The third has 8, but this is where we start seeing the transition. These are metals: sodium, magnesium, aluminum, silicon. These act like metals. They're semiconductors and so forth, because in the 4th level that can hold 16, or the 3rd level can hold 16, but will fill up with 8 and then go to the 4th level, and then you can start moving electrons up and down. What makes silica such a perfect element for transistors is its ability to move its electrons reliably from one energy level to another. And again, that acts as a switch, and we can treat those position changes as 1s and 0s and create store digital information and record digital information and interpret, read digital information. So that's why computer chips are made out of silica. It's not the only material that will do that, but it's the most efficient. We may find something better. Right now we've seen, again, revolution after revolution. I remember as a kid, I can't never resist this. When I was a kid, we had tubes in our TVs, right? Not only a big picture tube, but even all the circuitry was based on little vacuum tubes. And if one of them went bad, you had to take it to, usually it was like a 7-Eleven or something, it was a convenience store, and they had this big machine, and you'd plug your tube in there, and it would tell you whether it was good or not. It was a pain in the neck. Well, then they replaced those with solid state, with transistors. This was huge. I remember the first solid state TV. I was actually a freshman in college, I think, when my parents got that. And it was like, wow! And the pictures were clearer, and you could tune to the channel more easily. It was just so much better. Well, they still had a big picture tube. Most of you might remember the first flat panel TVs, right? The first flat screens that replaced the picture tube with a plasma or an LCD or LCD. I just said LCD. Anyway, LED or LCD screens, liquid crystal display or liquid electronic diodes. Those are what LED, LCD stands for. These are amazing new technologies, and now all of them are like this. I mean, look at the TV hanging up in the thing there. It's all flat, and they're big, and they're better, higher resolution because we can now make it all digital. There's silica chips in there. There's little computer chips in there. It's not a tube, and it's not a diode, or it's not a what do I just call it? Transistor anymore. Remember the little radios? You call them transistor radios. The first little radios. It was a revolution because they could use transistors and make it from a big box into a little bitty box. And now again, you've got a little. Remember, they don't sell them much anymore, but there's little bitty mini iPad, that could hold like 8 gigs of music in this little bitty square. They were too small, right? Just anyway. That miniaturization of things is due to our some new technologies. But the periodic table, these are a real element. I mean, these are real things. And you can find these in their elemental state sometimes, but most of the time they've formed compounds. We don't find just carbon. Now we do sometimes diamond and graphite, but most of the time it's combined with something else. It's carbon dioxide, or it's calcium carbonate, or it's a sugar, or a lipid, or something like that. And that's true of all these elements. Usually they form compounds. Sometimes we find them as elements, but usually not. Now again, I'm going to skip through this pretty quickly. I'm going to come back to most of this in the lab, because I want to talk about the types of reactions that we can get. One way of forming element or compounds and that lead to certain types of reactions are by forming ions. This is where one element gives an electron to another one in order to stabilize the two energy levels. That gives each atom a charge, making it an ion. And they stick together, but they also dissolve in water. The other way to do it is, and I talked about isotopes, so I'm going to skip past this a little bit too. All right, the other way to do it is for them to share the electrons in what's called a covalent bond. All right, let me get to what I really wanted to do most of this time, and I've been going off on these tangents that have addressed this, but I want to at least make sure that you've seen this. When we think about the atom as the basic unit of things, we already realize that's not adequate. Atoms are made of littler things, protons, neutrons, and electrons. Now, the electron, turns out, we can't get any smaller than that. We can't break an electron apart and find anything else inside of it. But protons, neutrons, we do. We can smash them together and find smaller things inside protons and neutrons. These are, and I'll show you a close-up of this in a little bit, these are these other quantum particles. And they're held together in protons and neutrons by other quantum particles called gauge particles that carry a force. So some of these particles carry a force. Now, that's not a surprise. We know the photon carries a force. That's a particle that carries a force. That doesn't surprise us. The strong and weak nuclear forces, I guess I can't enlarge it like I thought, come from other quantum particles inside protons and neutrons. The gluon brings the strong force. This is what holds those protons and neutrons together. The weak force then holds the nucleus together, not the particle itself, but the nucleus, the particles held together by the weak force. When we break a particle apart, an atom apart, in a nuclear reaction, it's these forces we're overcoming, and it's the energy in these forces that is released. We can also put an atom into a lower energy state in a fusion reaction. This is what happens in the sun, and that also releases a lot of energy. So both nuclear reactions, fission and fusion, release a lot of energy because these particles are carrying that energy into those and holding them in those bonds. The electron is what's called a lepton, and you can see that here. There are many others called neutrinos. We predicted neutrinos a long time ago, that there should be trillions of these things streaming from the sun, but they have such little mass, almost negligible mass, almost none, that they're very difficult to detect, and we've only recently been able to detect them. So we're still learning a lot about those. It's the quarks that are held together by the weak force or by the strong force in order to produce protons and neutrons. And then this is an old chart, because look down here. Higgs. It isn't up here yet. It was predicted. I'm going to show you a video in lab about just, again, why significant, why that's so significant. Now, where do we go from here? Because now there's a suggestion that this isn't small enough, that there's actually things inside these particles, even the electron and photon, called strings, that everything is a vibrating string of energy. Little bitty. I don't know why I even bother to do this, right? I mean, just to suggest how little they might be. But that's what the universe is made of, fundamentally. Now, we don't know that this is true yet, but we need something like that to explain the behavior of these particles. Why do they behave the way they do? Why is each particle different and unique? There may be twice as many particles. Again, we're going to talk about supersymmetry in lab. And if they're how are they each unique? Well, it could be that each one is a string vibrating at a different frequency. And so we're going to talk about string theory again later after Thanksgiving. All right, we'll spend a little bit more time on string theory. I am going to talk more about some other ideas first, though, and we'll catch up on that. All right. So we call these particles, all these different particles, a particle zoo. Leptons and quarks. This is what it kind of looks like when you smash them together and you see these things fly off in different directions, and you can measure these angles and the velocities of these particles and determine, again, their properties from that. And you can see some of them go in spiral directions, some go in straight directions, some sort of, again, spiral off in different planes, and so forth. So, I'm going to interpret it for you because I can't do that, but particle physicists can, and they can figure out what these particles are. But let me end with one more sort of, I think, amazing fact. If we look at there are four forces that we know of. And there may be more, but these are the four that are easy to see, easy to measure. The strong and weak nuclear forces, which we know are holding things together in the atom. The electromagnetic force, which holds the electrons in orbit and generates a flow of charge or magnetism, and all of it related together. And the gravity. And gravity is a pretty obvious force, right? We can't ignore gravity. The weak force, the strong force, and the electromagnetic force can all be associated with a particle. The gluon, the different bosons, the photon. But gravity has no particle that we can point to. There's no graviton. Maybe there's a graviton. Matter of fact, quantum physics predicts a graviton. And maybe we'll find one. Maybe we'll find it. But right now we can't associate gravity with a particle. Einstein defined gravity as momentum in space-time. And I haven't talked about relativity. I don't know if I skipped that lecture. Maybe I'll have to come back and pick that up. And that explains, again, how gravity works and whatever. But we have to find a way of putting the two ideas together, because we don't know really what gravity is, where it comes from. Again, we can predict it, we can measure it, we can manipulate it in some ways, not totally. If we can find a graviton similar to Higgs boson, maybe we can manipulate gravity. So we'll keep looking for it. But we also need to look for a way to explain gravity along with these other forces in such a way that we have one explanation instead of two. Right now we have two. We have relativity to explain gravity. We have quantum mechanics to explain the other three. There's got to be a way to put those together into one explanation. This is what we mean by a unified theory. The grand unified theory. What led... there's where I had it blown up, but I've already talked about it. Sorry about that. The grand unified theory, I thought I had a slide to talk about this. Oh well. Is what Einstein searched for his whole career and never really found. String theory is a unifying theory. If it's true, if it can be shown to be true, and it's under investigation right now, the experiments are being designed to test string theory, it could be the unifying theory that we're looking for. There are some other options, loop quantum gravity and some other things. Again, when you look at them more closely, they seem to merge. So physicists feel like they're getting closer and closer to this unified theory. And it's not that strange, if you think about it. Electricity and magnetism and heat were completely different forces. We had no way of thinking of them in one explanation until recently. Now we can. Now they're unified. We can explain them all using quantum mechanics. It explains all of it. So they've been unified. We just need one more step, and that's gravity. So we'll talk more about this stuff. I do want to end with this video. Well, bear with me, just because it's pretty funny. Actually, I'll give you, here's what I'll do. We'll do the quiz. I've got your tests. I'll play the video, and you can pick up your tests and go, okay? All right, so let's escape out of here real quick, get to the quiz. Yeah, I think I skipped over relativity side. We'll come back to that.
Oh, 17?
All right, that's right. We haven't done quantum mechanics yet. Particle zoo. Hold on.
Still on 15?
Is it still in here? Maybe it's still in, yeah, maybe it's in
Yeah,
here.
15.
Okay.
We're on 16.
Where's my particle zoo topic? Is it in the string theory chapter? No. Anybody remembers reading about this yet? Reading ahead? Yeah, I probably could. No, that's back to the beginning. Yes? What's that? Go where? Component? Oh, yeah. Students?
It's actually grid,
It's in grid?
and then it'll show you all of the,
All right. Show you all the quizzes here.
oh, but it's because you're the teacher, it doesn't show you the quizzes like on ours.
We finished 15. Everything
Right.
was true.
Yeah. All right, well, I apologize for this. We'll, let me try one more time and then we'll,
So it's 16.
is it 16? It's
Yes,
in
sir.
16? That kind of makes sense.
17. Oh, she just looked it up. She said what you're looking for is 17, but let's see. 'Cause he just
The last page of 17?
Particles
Yeah.
is 17.
All right. That's what I thought it was. I don't know why.
So we skipped 16, right?
All right, there it is. You're right. They had that quiz set up differently. That was weird. Threw me off. All right, here we go. Particle zoo. Sorry about this. It's going to be anticlimactic now. We are all swimming in the Higgs Ocean, and this is true. Again, I'll talk about this more in lab, but when there's a description of the Higgs field that describes it as the Higgs Ocean. And we are all swimming. We're all surrounded by Higgs bosons. I didn't know. Finished. Jeez. I'm not thinking straight today. I had some things in my... A hydrogen ion is simply a proton. This is true. If you take a hydrogen atom, which is a proton surrounded by one electron, strip the electron away to make it an ion, all you have left is the proton. All right, a quark is charming. If you remember the chart of quarks and leptons, one of the quarks' name is charm. One is strange, one is up, one is down. So in a sense, yes, quarks are charming, because one of the quarks is charm. So this is funny. All right, and the graviton, if it exists, may be able to travel through more than just the obvious 4 dimensions. This is true. We'll talk more about this with string theory, because this could explain a lot of things about gravity. But we need 11 dimensions first. All right, there are neutrons in the particle zoo, but not zebras. True. Right. They are not zebras. There are neutrons. They're not zebras. Okay. All right, finally, done. Okay. All right. I don't know how I managed to navigate through that without making any mistakes, but I did. All right, I'm going to play this video as I pass out the tests, because it's really funny.
There's a collider under Geneva, reaching new energies that we've never achieved before. Finally, we can see with this machine a brand new canopy of 125 GeV. See how gluons and vector bosons fuse. New arms and gamma rays emerge from something new. There's a collider under Geneva, making one particle that we've never seen before. So, a complex scalar, elusive boson, escape detection by the Lepton teletron. The complex scalar, what is its purpose? It's got me thinking we could have heard of more.
You get the point. There's a funnier one that I'll show you about string theory. Rich, personally. He's a grad student. Okay, I think. Okay, what's his name? Boucherie. All right, so I've called Sandra Batula, Keith Baker, Brianna Basie, and Evan Bernstein. Okay, all right. Could you hear me better back there, even while I was looking down at the ground? Nisha Brown. Dennis Bueno. Elizabeth Campbell. Ivan Canales. Cedric Davis. Andre DeFreitas. Noemi Garon. Delvia Gomez. Jennifer Gonzaga. Jennifer Gonzalez. Aldair Hernandez. Gal Watt. Put this over here. Peyton Hernandez. Coming down the right side, I'll try to put it over here. Kimberly Hurtado. Nelson Hurtado. Amir Ismail. Yamel Armillo. Jose Hernandez. Susan Curran Kelly. Amar Khalil. Muhammad Khan. Paris Corral. Alia Katab. Crystal Lewis. Kevin Lopez. Elvira Lozano. Char Lockett. Eric Lopez, sorry. Audrey Lopez. Julio Luna. Maria Lucio. Tabitha Munstavine. Christina Mobagar. Rachel Fiolu. Van Nguyen. Bernicia Osborne. Derica Ramdu. Stephanie Rodriguez. Diana Valdez. James Ramirez. Karina Reyes. Are you hanging in there? Diana Sanchez. Holly Sire. Michael Tran. Some of them are Alex Tyson, out of alphabetical order. Alex Tyson. All right. Jamel White. Joy Williams. That's yours. All right. So these are out of alphabetical order, maybe because they didn't have a space on. Ashia Wallace. Okay, 98. Andres Caneras. Juan Perez. Jennifer Lajano. Olga Hernandez. Fares Painter. Guadalupe Garcia Castillo. Alessandra Ducati. Del Raylan Dolphus. Emmanuel Deborah. Stephen Salinas. Faith Pruneda. All right, the rest are incomplete.